what is MPI to begin with? So this slide hasn't changed in a long time. It's a message passing library interface standard, and that's all three of those words are important. So it's a specification, it's not a particular implementation. And it's a library, not a language. So you link to it rather than run it through a compiler. And it implements, at least from the beginning, until it gets a little fancier, the classical message passing programming model in which separate processes communicate with pairs of operations and sends and receives. So MPI-1, we refer to it as MPI-1, was the first MPI standard. It was defined over the years 1993 and 94 by a group of parallel computer vendors, all of whom were looking for a standard way to program their new machines, computer scientists and application developers. And Bill and I were in that group. I think Rajiv joined shortly thereafter. And that was a very interesting experience. I've often said I think one of the reasons MPI was a success is because of the hotel that we met in. We chose a really terrible hotel in the wasteland of North Dallas. And we met every 6 weeks, so it was a fairly intensive process. And going there was so unpleasant that no bystanders or curiosity seekers or people who wanted to just watch the process, those people all dropped out after a while. So it was a very serious group that survived to the end. Implementations appeared very quickly. In fact, Bill and I would say one of our contributions to the process was to keep a running implementation of the standard as it evolved. You know how you're never supposed to write the program until you have the specification. We did exactly the opposite thing. The standard changed every 6 weeks. We'd have a new meeting and people would have new ideas and they'd decide old ideas were bad. And we would cheerfully throw out what had been implemented 6 weeks ago and implement the new stuff. And that helped. That helped flush out ambiguities in the standard, especially. Sometimes you can't tell what a standard means until you go to try to implement it, because the code is so much less ambiguous than the English language is. And then that meant that when the standard was finalized, then our last iteration was the first implementation. So it was available very quickly. Now it's taken for granted on all parallel machines, and you can get free portable implementations. MPICH happens to be ours. OpenMPI is another one. So as I said, it started sort of announced at Supercomputing 93 with the basic stuff that you're familiar with: point-to-point communication, collective operations, data types, communicators, et cetera. MPI-2, MPI-1 was met with two responses. One is it's too big. There's too much stuff in here. I think it had 128 functions. Other people said it was too small because it was leaving things out. So we tried to add some of those things in MPI-2. So 3 years later, MPI-2 added parallel I/O, the first round of remote memory access stuff, C++ bindings, thread support, dynamic processes, and so forth. And then the forum disbanded, and there was a time of 10 years of sort of peace and getting people used to using MPI as it stood there. After that time, there were, the machines changed. The people got very used to MPI, and they saw what needed to be done to both fix a few things that had been discovered really were not quite right in the standard. And so the forum began meeting again, and in 2008 and 9, there were clarifications and fixes, and in 2012, some really major stuff was added to MPI. And that will be the subject of the MPI 3 session tomorrow. And then this year, there have been again, some small updates to as the result of experience with the MPI-3 stuff. So now I'm going to go back to being really basic and talking through the basic ideas of MPI at the idea level, not at the syntax level. So first we have to decide what we mean by a couple of terms. So when I say process, what I mean by that is an address space, a program, one or more threads of control. So each of the threads has its own subroutine call stack and separate program counter, but it shares the memory. The memory belongs to the process. So they share this address space, and shared memory has both advantages and disadvantages, as I'm sure you're familiar with. So an old-fashioned Unix process is just a single-threaded process. And in MPI-1, we thought of a parallel program. An MPI program was a fixed-size collection of old-fashioned Unix processes with a single thread, and we identify those with an integer that's an MPI rank. It was never the case that MPI was single program, multiple data. Some people think of it that way. They think of MPI programs as SPMD programs or BSP programs, bulk synchronous programming. MPI from the very beginning did not have that restriction. So the individual MPI processes can be running different programs because process is a program, has a program. In MPI-2, we allowed MPI processes to be multi-threaded. You have to add some stuff to make it safe to use MPI with with multi-threaded processes. And we'll talk about that later this week in the sessions on hybrid programming, where we mix thread programming either with pthreads or OpenMP and MPI. And we also added the ability to add more processes at runtime, so the number of MPI ranks is not fixed. So sequential programming is one single-threaded process. Parallel programming, well, there's different kinds of parallel programming. One process with multiple threads. You heard a lot about that this morning, either with OpenMP or pthreads or TBB, or there's lots of different kinds of threading things. Or it could be multiple single-threaded processes. That's the MPI-1 view. Or multiple threaded processes as allowed in MPI-2. So to the dedicated MPI programmer like me, shared memory parallel programming is hard. Some people say, oh, it would be so much easier if we had just a shared memory. Not so hard, not so easy if you've ever debugged difficult problems on shared memory. At the same time, processes do have to communicate, or else you just have a collection of sequential programs. So what MPI is for is communication among processes. That is, it's for moving data from one address space to another. We'll generalize that a little bit, but that's the basic idea of what MPI is for. Now, what makes MPI a solution for the problem of shared memory is that it allows data to move from one address space to another, but it very strictly controls exactly how that happens. So we have these address spaces, and when this process does an MPI receive, he is saying, well, everybody else stay out of my memory. I'm not sharing that with you. But during the time of this call, this specific piece of my memory, I'm going to expose to someone else. They can write in it. And the MPI send is then allowed to write in that receive. So it's limited in time and space. Space is the buffer that you give it, and time is the duration of the MPI receive call, if it's a blocking call. The non-blocking operations expand this window in time, but not in space. So when you do an MPI I receive, you say the memory that you're allowing people to write in, but you're leaving it open for a little bit until you do the wait, and then at that point, you've closed the time window again when people can write in it. So now let's talk about non-blocking communication. What it does is it's exposing part of its address space to the system, I'm going to call it, because from the programmer's point of view, the system contains operating system code, MPI implementation code, maybe non-portable communication hardware and software, all the different guys who are not me that might be messing with my memory, including other processes. So what MPI is doing is exposing, for a short time and a small space, your memory to those other processes. That's what makes MPI programs typically easier to debug than shared memory programs when you don't know who it was that wrote on your memory and at the wrong time or in the wrong place. So the system might use its internal buffers. They might be not the same as the application's buffers. You might give the system a big buffer, but its hardware has small buffers, so it might have to do many movements across the network to pass your whole buffer to another process. So the receive exposes the address space. The send, the non-blocking send, says where the data is on my side and says which process's receive buffer it's supposed to go to. And so it's turning its buffer over to the system for it to read. So both buffers at this point belong to the system. And the wait on both sides closes those windows and sort of takes that memory back for you to use. And what that means is the receiver has received the message and can now use it, and the sender has sent it, and he's no longer responsible for it, so he can reuse that send buffer, put something else in it, and send it to someone else, and so forth. So that's what the wait does, is close that time and space window. So the blocking operations, which are probably the first ones you learn about, are actually somewhat dangerous. And in fact, in one version, the standard didn't have blocking send and receive, but we felt that we had to include them because so many people were used to using them. So why are they bad? What is the danger? Well, there are two dangers. One's the deadlock danger. So suppose you have two processes and they just want to exchange something. So he does the send and he does the send. Well, now when you send something, you're turning that buffer over to the system to use, and you don't get control back until it's done with it. Well, it's guaranteed that for some size of message, probably unknown to you unless you know a lot about the system you're using, this will block because this send can't really complete while this send, the sends can't complete until somebody can be done. And the system can't hold both of those messages at the same time. So for some large size message, for one of the vendors, that large size was 0, but for most vendors, it was big. A simple exchange like this will deadlock. So deadlocks if the system can't absorb the messages, then thus allowing the send to complete so that the receive can get posted. And there's also a performance danger even when there's not an exchange. So this process does a send and the receive comes much later. Well, again, if the system can't absorb this message until it's got to receive to put the data in, possibly piecemeal, then the send will block and until the receive happens, and that might be much later. So the solution to these two dangers is to use the non-blocking send and receive. So it solves both problems because as soon as you post the receive, you're telling the system, okay, here's a place where you can put an incoming message. So you post the receive that supplies the buffers. Both of these sends can then immediately proceed because the destination is available, and then you do the wait to finish it off. And same sort of thing with the performance. If you post the I receive early, so that as soon as the send happens, that can be happening until you wait. And in this example, I've used the I receive supplies a buffer on the receiving side. Well, there's a corresponding way to supply that buffer on the sending side. And if you've ever used the B send, that's what the B send is for. It's to define a place for that. You're giving the system some of your memory for it to use on the sending side instead of the receiving side. So let's talk about this idea of overlapping communication and computation. A very common misconception about MPI is that the non-blocking operations are there in order to allow simultaneous communication and computation. And many people expect then this to happen, and in very many cases, it doesn't. And that's because the idea of the non-blocking operations is to allow this, but it doesn't require it. So but the real purpose is what we've done before, to avoid deadlock or performance problems. So one way to realize how little is actually specified is to think of the different ways an implementation can meet the standard for non-blocking operations. I think what a lot of people would like is for it to use a system thread or hardware support or communication engine of some sort in order to move data in parallel with local computation between the non-blocking operation and the wait. So you post the non-blocking operation, and then if data motion is expensive because you have a lot of it to do, it happens, you can compute during the time between the I receive and the wait. But the standard doesn't require that. So there are a couple of other things it could do. It could start the communication when you post the receive and the I send and the I receive, but it may only move data if you do some other MPI call in between. So MPI has control. You give it control, it looks around and sees that there's a message in transit and it moves it along or moves another little bit of it or something like that. If the system can absorb the message, or if the I receive has been posted, you could complete the operation during the I send. That may or may not be what you want, but standard conforming implementation can do that. It can even delay the initiation of the process until it sees the wait. It just has to get the data moved according to the spec. But it doesn't require that there is some way of having the communication occurring while you're computing. So it's a good time to sort of summarize the different kinds of send. So the MPI send blocks until the message has been absorbed. So when you get control back from the send, then you can reuse that buffer. The MPI I send doesn't block. It just tells the implementation that here's a buffer that you want to send to a specific rank. The synchronous send, for those of you who have used it, it blocks until the matching receive has been posted. It doesn't block until the data has been received, but it blocks until that buffer has been made available on the receiver side, until that's been identified, so that it has a place to start putting these bytes. And the R send, says the R is for ready. It assumes that the receiver is ready. What that means is that it can start firing things off over the network to that rank with the assumption that when the data gets there, that MPI process has posted the receive, and so there's a place to put it. So The programmer is responsible for this, so if you do an rsend and the receiver hasn't posted the receive, very unpredictable and bad things can happen. But this is a situation that's useful enough that this is included in the standard. So one way to use it is if you have two processes and one asks a question of the other one, say. So you might post the receive for the answer before you send the question. Well, since you wrote both sides of this, you know that the code for this knows that the receive is posted, so he can, after receiving the question, he can do an rsend of the answer because he knows he couldn't have received the question until after the receive for the answer was posted. So that's how the programmer can be responsible for making sure that the iReceive is posted and is available to receive the iSend. Just want to say one small thing about collective operations. As you know, there are a lot of collective communication patterns. Some of them have computation inside them, and you can make up your own collective operations. So there's a lot of capability in MPI's collective operations. Those are the ones that are called by all the processes in a given communicator. And the algorithms that are used in implementations are varied, and they depend on the message sizes. You might change algorithms at some point based on the size, the machine topologies, the things that the machines can do. So the scalable algorithms for collective operations is still a research topic in the area of MPI implementation. One thing that some people miss when they're timing their MPI, this sort of pattern happens a lot, that everybody computes for a while and then they do a collective operation. Maybe they're going to compute the residual or something like that. So they compute, then they do, say, an all reduce, in which everybody's going to get some collective data item that's the result of some computation across all the nodes. And they time this with their profiler, and they say, oh, all reduce is slow on this machine. All my time seems to be spent in all reduce. This must be a crummy implementation of MPI to have this terrible all reduce. And what happens is that that's an unfair accusation on the all reduce, because it can easily happen that you have a load balancing problem, not a slow all reduce problem. All reduce can't complete until everybody has made their contribution. So if the computations on different nodes take a different amount of time, it isn't the case that the all reduce was too slow, it was that one of your nodes was too fast. And so, of course, it took this much time because it had to wait for the all reduce to start here. So that's just a thing to note about tuning collective operations. So MPI-2 introduced dynamic process management. That is, there's an MPI spawn by which one MPI program can add more processes to itself. It's one of the things that's often not implemented on the very largest machines, because the creation of new processes means that the operating system has to get involved, whereas for most of MPI, only minimal parts of the operating system need to be involved. So although it's something easy to do on clusters or even laptops, it's something that's difficult to do on a blue gene, for example. You can't do an MPI spawn on a blue gene. So MPI-2 added that, partly because people who had used PVM at the time were puzzled as to where processes would come from. The idea of starting them up outside the library was a new thing. So to compete with PVM, we introduced dynamic process management, and just about the time that that solution arrived, the problem went away. People started using MPI instead of PVM. Introduced parallel I/O. We'll talk about that a little later in the week. Thread safety we'll talk about mainly tomorrow. bindings for C++. The original had bindings for Fortran 77 and C. The C++ bindings came in. They were there for the 10 years. No one seemed to use them much, so in MPI-3 they're gone. So we're not going to talk about dynamic process management, as I just said. I'll just say one or two words about the one-sided operations.
Can I ask a question, sorry? So even though from the standard the C++ binding specification is gone, most implementations of C++ most implementations of MPI would still have C++ bindings moving forward, wouldn't they?
Well, I think you might find that to be the case now. I have two things I want to say here. So, but as things go on, if it's been deleted from the standard, it eventually, no one's going to work on it. This doesn't mean you can't use MPI programs, MPI in C++, you're using the C bindings, just like you would with lots of libraries. But in MPI-2, we introduced very specific C++ syntax for MPI send. You know, a send became a method on a communicator and some stuff like that. That's what's gone away, not the ability to use MPI and C++ programs. So that's sort of what happened as we observed during this 10 years, that that's what people were doing, not using the special C++ bindings. One of the reasons was that the C++ bindings that we did do were very much like the C bindings. That is, there was sort of a correspondence between the C++ calls and it was just a little bit of syntactic stuff to make it look more C++ like. Whereas the C++ enthusiasts would rather have a much different looking library that didn't look like the C library. And there were a couple of things. There was something called MPI, and there's a system called Boost that do provide much of the functionality of MPI in something that looks much more like native C++. So the one-sided operations can be thought of as in the following way. We talked about how in MPI-1, the communication buffer and the call that specifies that is really saying where and for how long you're exposing part of your memory to the system, either for something to come in or for the system to take something out. So a window object is attached to a single process, and it's a generalization in the following sense. What you're doing is making a larger amount of space available to other processes, and you're letting multiple processes write in there and take things out, and the window can be open for a long time. So it's not shared memory, it's just a generalization of the parameters for exchanging data between address spaces. So we'll talk about this at some length tomorrow, but I just wanted to point out this analogy that it's not that different. It's just when you allocate a window object, you expose a larger part of your address space, and usually for a longer time, and multiple communications can use this window, different parts of this window, and it separates out the buffer allocation, the data movement, and the synchronization become separate operations instead of being combined like they are in the send and receive. So the operations are creating a window. You can put data in someone else's window. You can get it from someone else's window. And you can do computations with the accumulate function. And there are multiple ways to do the synchronization. We'll talk about that tomorrow. Parallel I/O we'll cover later in the week when we talk about I/O and file systems in general. But its philosophical principle is based on this analogy that when you read from a file, it's a bit like receiving a message from the file system. And when you write, it's a little bit like sending a message to the file system. And the things that you want when you read and write data are very much the same sorts of things that you want when you send and receive data. And so the MPI I/O operations borrow the MPI machinery to do that. So one of the things that you need to do in file systems is to write non-contiguous data. Write it maybe perhaps from non-contiguous parts of memory to non-contiguous parts of the file. Well, MPI-1 has MPI data types to define non-contiguous chunks of memory when you define, because buffers do not have to be contiguous. So data types are used to define data in memory and files for the I/O operations. There are non-blocking I/O operations absorbed into MPI. They look very much like the MPI non-blocking operations. And there are also collective reads and writes that use the machinery of and the syntax of MPI collective operations. So we'll talk more about that next week. And then the MPI-3 stuff, there was a special session on tomorrow. Okay, so that's the end of the first 3/4 of my talk. So maybe this would be a good time for some questions about MPI. Maybe I haven't told you anything you didn't know. I was just hoping to get you to think about it a different way. Yeah.
So when you said, when you use MPI send or I receive, the small window of memory is open, right?
Yes.
Is it open only for, let's say, the process we want to send or receive, as compared to when you said one-sided, we still open a window that can be accessed by any process?
Yes.
Is there a difference between these two?
Yes, that would be one way to think of it. So it's both in space and in time. So when you do a receive, you're expecting one message to come in and satisfy that receive. If you open a window, then you're allowing other processes to do puts into that for quite some time, perhaps. And different processes can put different things in different parts of your window. So it's just a generalization of having this smaller window with one that's satisfied by one message transfer. Okay? So let me say a little bit about this implementation, which we're sort of hoping that you can do some of the exercises that we'll talk about just on your local machines or your cluster back home or whatever. So this is this project was started, as I was saying, during the early days of the MPI forum meetings. So it's been the research vehicle for Bill and Rajiv and I and quite a few other people on research topics in MPI implementation, but it's also a high performance implementation. That's what our research tries to do. And it's very portable. It gives you all of the features of MPI that have been defined so far. In turn, the very latest MPI-3 stuff is in MPICH. And it is the foundation for almost all vendor MPI implementations. MPICH is architected so that an awful lot of the code is portable, and the parts that are going to be specific to the vendor's own hardware or low-level message passing API are isolated in a way so that it's convenient for vendors to adopt it and port it to their machines or optimize it for their machines. And it's still an active development project led by Argonne, Rajiv, and University of Illinois, Bill. And we have lots of other close contributors who help with features and bug fixes and so forth, and you may become one of those contributors. And those contributors include both universities and vendors that we work very close with. The current release is called 3.1.4. So you can think of it as Pi, I guess. So you can run the experiments that we're going to talk about tonight or tomorrow on your Linux or your Mac OS laptop. So these slides are on the web if you go to this talk and where it says, I think it says more info on that page. and you can see these slides, so I don't have to have everything on the same slide because you can look at them this way. But just to indicate how straightforward this is, go to our website, download it, you'll get a compressed tar file. So what we're going to do is build it from source. So untar it, you'll get this directory, 3.1.4. We use configure to make the installation portable. So you have to say a directory where you want it installed, so because that'll be specific to you and the machine that you're installing it on. You can watch it being built if you do this, and keep a record of it so that if something goes wrong and you want to show us, you'll have this file to do it. So configure, make install, standard sort of steps. And then you will get some executable files for compiling and running MPI programs. So those are going to be put in the bin subdirectory of this directory that you told us on the configure. So that's an important connection. So you add that to your path using whatever shell that you're using. If you don't have a Fortran compiler on your machine, sometimes people don't have them on their laptops, then on the configure say that you don't want Fortran, and then you won't get Fortran. The way you compile and run things is with substitutions, substitute commands for compiling. So for C programs, you say MPI-CC. What that will do is that will call a compiler that it found on your machine during the configure stage, and it will link in the libraries that it has installed, and so you don't have to worry about very many special commands. Just treat it as your C compiler that knows where the libraries are that you might need. So we haven't removed the C++ yet. So if you want to do that, you can use MPI CXX, Fortran 77, Fortran 90. If you have to link in a library, the MPI CC script can certainly take that. So you're just thinking of these commands as substituting for your usual commands for compiling and running a program. You run it with the command MPI exec. MPI exec was recommended as a part of the standard, but it's not required. So some environments you can require to use MPI run or MPICH run or various sorts of things. But for MPICH, MPI exec is it. Say how many processes you want, and that's all you have to do. So if you're running on your laptop, you can do something like just specify how many processes you want. If you're running on a cluster, you can specify the hosts that you want to run on and how many processes you want on each one and so forth. Various kinds of, various syntax for specifying what runs where. Or you can create a file that has this information in it and then run with the host file command that as described in the bottom. So there are various things you can do. When you download MPICH, you'll have an examples directory. So there's a lot of stuff in there for trying out different parts of MPI. One of the oldest parallel programs is called CPI, calculates the value of pi. And the output will show you the processes that are running and what hosts they're on, as well as calculating pi, because that's probably more interesting to you than the actual value of pi, which you probably know. And you can try it with multiple hosts. Pardon me?
Hint, it's the same as the MPICH version. Hint, it's the same as the MPICH version.
I see. Ray is saying the value of pi is actually the one, is correct, is the one that the example will compute. And if anything goes wrong during this process, So at least for the next couple of days, you can talk to Bill and Rajiv and me. Afterwards, send an email to discuss a lot of people on that mailing list. So MPI exec all by itself works on your cluster or your laptop with various resource managers like you'll encounter on Vesta. You will need to do some other stuff. After dinner, maybe Ray will tell us a little bit about how to do that on our Blue Gene. You probably already told them that yesterday, but they'll be newly motivated today. Yes, so here's the stuff for how to do it on Blue Gene. Here are sources. You can always look up the standard. It's available at mpiforum.org. There's an MPI webpage that we have at Argonne that is the MPI webpage, not just the MPI CH webpage. Also, we keep a lot of tutorials. We've given tutorials at Supercomputing for many years, and the slides for those tutorials are there, so there's many more things you can learn. There are 2 new books written by Bill, Rajiv, me, and Torsten Heffler. These just came out last fall. This is the 3rd edition of the original Using MPI book, and this new one covers both the MPI-2 stuff and the MPI-3 stuff. So, so full disclosure, each of us makes a nickel or something like that when you buy this book. So you probably need a couple copies for home and a couple copies of. There are some examples that you can start on tonight if you want, but we'll talk about them more tomorrow that are in Bill's directory at U of I.
Especially for tomorrow for the exercises, just like if we have open MPI or something on our laptop,
Should be fine, yeah.
what are the differences?
So the question was, if we have open MPI on our laptops, does that make a difference for the exercises? It should not. I don't think it will. I use open MPI on my laptop. It's not an inferior implementation. If anything goes wrong, I can't help you, but with MPICH, I can. So that's the big difference. And what was your second question? Or was that the second question? What's the difference? So in theory, you shouldn't be able to tell the difference. I have not had any bad experiences with OpenMPI. So I would say don't worry about it. Install MPICH for fun. So it's fun to, yep.
Good question. Going back to slide number 24, you said that if you want to run it on our computers, we just got to run MPI exec with -np16, for example.
Right.
That, I'm wondering, most of, it's a wild guess, but based on what I can see, most people have an Intel i7 in the room on their laptops. An Intel i7. That's a wild guess, but
What I'm missing that.
I'm an
i7 processor.
Yeah, like
Intel i7 processor.
Oh, I see. Yeah, okay.
I'm sort
Sorry.
of assuming widely, obviously. Now, my question is, for the sake of performance measurement, how would hyperthreading affect our results?
So it can be sort of tricky. Depends on, at least my experience with, so I have a fairly old Apple here with 2 cores and 2 hyperthreads per core. And I find that when I run what looks like a perfectly load balanced program, it isn't that way. So the operating system is shortchanging some of the hyperthreads, and in a way that I don't completely understand. So I don't do any performance measurement on my laptop.
I think that's the OS. That's more the OS. If you run the same thing on a perfectly empty machine, you should get it. You should get the balanced execution, right?
I think the answer is, don't worry too much about the performance on your laptop. If it's running correctly, go to Vesta, which is a very, very uniform, balanced machine that gives very predictable results.
So basically, laptop would be a measure of correctness of our code, and then for real performance, we should deploy.
It's a handy development environment. I mean, if you're sort of masochistic, you can do your development on Vesta too, but but you have to wait in the queue.
What governs the maximum value that you can pass to -NP on your laptop?
You know, I don't think I've ever experimentally determined that, but I can try it if you want.
Well, I know that with OpenMPI, the maximum is 48 on my laptop, and I don't understand why.
I would say it's probably arbitrarily put in the implementation. Do we have such a limitation?
No, but there will be limitations that come from the available number of FDs, a couple other resources that you can exhaust.
More than 48?
More than 48. But once you're oversubscribing, performance will be really awful. It's no longer truly parallel, right?
No, I understand the question. I'm sure that what I was asking Bill and what he answered is there's no place in our implementation where it says if NP is greater than 48, abort. There's nothing like that. You're free to abuse your laptop to your heart's content. Okay, thanks.